the degenerate point is interpreted as a location of a particle. And then such configurations, degenerate configurations, also appear in the torsion form idea invoked by Hansen and Regé way back in 1978. However, to understand the role of the zero determinant phase in quantum gravity concretely, one could explore a Hamiltonian analysis which would then help us towards a quantization. Right? However, there is a problem. The standard ADM parameterization is essentially built upon inverse tetrad fields and hence is not a suitable framework in this regard if one wants to develop a Hamiltonian theory using the ADM parameterization. So now what to do? So these are the questions. Firstly, how to proceed? How to define the variables when there are when the tetrad or the metric is not invertible? What happens to the constraint structure and what happens to the algebra between the constraints, and then how do you count degrees of freedom? All those questions come one after another. Okay. Also, a relevant or related question is, are the theories where the determinant of the tetrad is exactly 0 and the theories where it goes to 0 in a limit, are these theories equivalent? In fact, such limits have been talked about in the literature, and one special case goes under the name of Carolian gravity. Also, then one can ask, could the quantization of gravity in this phase be any simpler than what we know for invertible metric case? And then, of course, how to relate the two cases? That question has to be answered. So anyway, let us try to attempt the first question, that is, how to approach this problem of doing Hamiltonian gravity with non-invertible or zero determinant tetrad or metric. So the natural way to proceed is through the first order formulation, which is well defined even if the tetrad are not invertible, because you don't need inverse tetrads anywhere, unlike Einstein-Hilbert action. Okay. So now, in order to go to the Hamiltonian theory, one does the standard space-time split, and the variables marked in red here in this line are the canonical variables. So you have the tetrad and their momenta, and connection and their momenta, and then some constraints. So there are primary constraints because some of these variables are not independent. So it's not essential to go into the details of what are they, but it's obvious from this form what are they. So these are the primary constraints which relates the coordinates and momenta through this kind of a generic relation. Okay. However, what is the difference from this case to the case of standard Hilbert-Palatini gravity where tetrad is invertible? So in standard case, we can always invert this first primary constraint between omega momenta and E coordinate to get rid of these tetrad fields altogether and go to a pure connection formalism where all you have is this omega and pi, and these guys go away. But here you can't do that because the tetrad are not invertible. So you have to carry these tetrad fields along and then see what happens. So that's the first difference. So now there are also secondary constraints because there are Lagrange multipliers, these time components of the tetrad and the connection. So these lead to the secondary constraints. So the first set of secondary constraints is essentially 4 in number. They are a combination of Hamiltonian and space diffeomorphism constraints, and the other 6 GIJs, they are a combination of the rotation and boost. All these are well known, just that these are written a bit differently in these variables. So now with these primary constraints, one can write down the primary Hamiltonian density, where these are the Hamiltonian plus diffeomorphism, these are the rotation plus boost, and these are the primary constraints, 3 sets of them. Now for later convenience, what one can do is, one can rewrite these 18 primary constraints between omega momenta and E coordinates, and they can break up, these can be broken up into 12 and 6, okay. So the 6 of them can be written so that only these pi's appear but not these coordinate e's, and then the rest. And that has an advantage which I can't go into the detail of, but one can discuss later what is the advantage. So anyway, once you have this full set of constraints, it's easy to see what is the Poisson bracket, and in particular what are the non-trivial Poisson brackets. So these are the second class pairs, and I have marked the first one in red because this is what is the critical thing which would be useful for us. So if you check the time evolution of this constraint, which has to be consistent because it has to give 0, so you end up with this expression. Okay. Now in standard Hilbert-Palatini gravity for invertible tetrads, you have this piece which gives you another secondary constraint. Okay. And this is arbitrary. However, there is another possible solution where you can have this to be 0, which is the time component of the tetrad, and which corresponds to degenerate tetrad, because these are four of them being 0, so one full row or column is 0. And then this may be non-zero, which is different to standard constraint analysis of Hilbert-Palatini gravity. So this is the case we want to consider. So that's what is written here. For invertible tetrad, one obtains a secondary constraints, which implies essentially the vanishing of torsion in vacuum. However, the other possible solution corresponding to 0 determinant is that this ETIs, they themselves are 0, and then you don't have this secondary constraint anymore, so you don't have vanishing torsion in general. Okay. So in that case, where the determinant is 0, this pair then remains second class, okay, and that's what we have written here, and that is in contrast to the invertible case. So that's another difference compared to the standard case of invertible tetrads. So now we know the algebra, so let's count the first and second class pairs and fix the degree of freedom count. Okay. So we have essentially 12 second class pairs, and we have 4 second class pairs in this line, which are 6 CABs and 4 CIs. So 4 of them are second class and 2 leftover CABs are first class, which have vanishing bracket with this rotation and the phi A primary constraint, which are the only remaining constraints. So what you have is, so the rotation and boost and the primaries, these 3 primaries, they are again another 9 first class constraints. So altogether, when you count, there are 30 canonical pairs which come from the tetrad and its momenta and the connection and its momenta, 12 plus 18, which are 30. And then here you have 11 first class and 16 second class pairs. So this gives the count that you have 30 minus 27, which is 3 degrees of freedom per space-time point. Okay? And this is an important contrast to the invertible phase of first order gravity in vacuum, which corresponds to 2 degrees of freedom. And that comes essentially because the constraint algebra have changed in the middle. A point which I have already emphasized in the previous slide. Okay. So now one can fix the boost freedom through time gauge, and then one can go to a simpler set of constraints. However, there is a difference now compared to the usual Hilbert-Palatini case. The Hamiltonian constraint now acquires another extra term, which essentially comes from the connection variables. Remember, torsion is not 0 anymore, so these n's are the torsional degrees of freedom essentially, but non-dynamical, because they don't appear with derivatives. And then their corresponding momenta are 0. Okay. So now one can actually fix the Hamiltonian constraint by fixing this torsional scalar through this constraint. So this constraint can be strongly implemented, and then this torsional scalar combination can be fixed in terms of the basic variables here. And that takes away the Hamiltonian constraint essentially. And along with that, one can set the corresponding momenta, associated momenta to n to be 0, and that doesn't affect any of the remaining constraints. So with this, the scalar or Hamiltonian constraint is already solved, and that has simply disappeared through this torsional gauge fixing. And the final phase space, which has the coordinates q and momenta e, which are essentially densitized strads, so they are subject to the first class constraints, which are just the rotation and the space diffeomorphism. Boost have gone away because we have fixed the time gauge. Okay. So what are the main results? Yes, I'm at the end of my talk now. We find that the Hamiltonian theory of gravity at the zero determinant phase exhibits 3 local degrees of freedom. And this result doesn't depend on whether the null eigenvalue lies along the time or space direction. Okay. The details appear in the paper. And also for any finite e, the degree of freedom is 2, and this is also 2 when you go to a limit where the determinant tends to 0, which is known as the Carolean limit. Okay. So what this tells us is that the limit determinant e going to 0 has a discrete discontinuity, and this is analogous to the v dvz discontinuity for massive gravity, where for a non-zero graviton mass there are 5 degrees of freedom, whereas for a 0 graviton mass you have 2 degrees of freedom. Okay. So this is similar in that sense. So now the disappearance of the Hamiltonian constraint here in this case, non-invertible tetrad case, is an inviting feature, okay, because formally any functional invariant under internal rotations and diffeomorphisms are solutions in the quantum theory, of course up to other issues. And there are of course interpretational aspects of the candidate solutions for quantum states, and these have to be explored. Questions like, what is the connection of these zero determinant states to the Einsteinian phase? Are they connected through some perturbation or what? And of course, what are the possible contexts of relevance of this kind of analysis? These configurations are, or rather solutions, are expected to be relevant in the short distance or strong gravity regime and early universe scenarios close to singularity, and also as I said, in the context of BKL behavior in cosmology. And these issues, if explored in sufficient detail, may help us understand if this non-invertible metric phase indeed has a physical importance at all. Okay. So thank you for your presence and your attention.
Thank you. There is not enough time, so just one question, if there's a question.